Hi, my name is Stephen Burns. I'm a geophysicist with geometrics, and today we'll be going over field operations using the Atom Seismograph. This is part 3 of the Atom Seismograph video training series. We'll use two different software modules, SPACPlus and WaveEq, both programs within SeisImager SW+, to learn how to process shear wave velocity data and H/V data. To process our data, we'll open SPAC+. We'll go full screen. We are going to open a new folder. And that's going to be on the desktop, and Atom data, and Atom field operations training video. We have 11 seismographs. And here's our data. Now, you can select a single sensor. If you use Shift and the arrow keys up and down, you can move between those sensors. You can also move sideways. And this is basically selecting the data that you'll be working with. So these are our one component atoms. You can see the serial number on the left right here. And they have just their vertical component. At the bottom is our 3-component atom, the atom 3C. And you can see that serial number, and you can see it has the 3 components here. So we're trying to do a velocity, shear wave velocity survey, and we're trying to analyze it. So we will go to Edit, and we'll select Multiple Sensor. What we're interested in is common time block data. And common time block is basically a point in time where all the seismographs are on. Now, I was doing triangular surveys here, so there's only one single common time block here, and it's just a mistake. What we're interested in is this data here on the right side. And we can see that since I only used 10 seismographs, serial number 64 was turned off for the duration of the survey. So if we want to select this data, we can go to File, and we can go to Advanced Options, and we can go to AU box ID to ignore, and we'll type in the serial number of atom 64, so 100064. Now we see we have 2 common time blocks. And this is the common time block that we are interested in. This is the data that I would like to process for this training video. If I wanted to do H/V processing, which I'll do, then I would just again hit single sensor, and I can shoot over to that 3-component data from that survey. But we're doing the shear wave survey first. So we're going to click this. We're going to click common time block and go to the next screen. Now it's asking us, do we want to select a single component? This is a velocity survey, a shear wave velocity survey, and I only want to select the vertical component. So I'll select yes. I'll choose as much vertical component, hit OK. And do I want to apply a bandpass filter? There was no noise at this site. It was very nice, and there was no electrical or anything, so no bandpass filter. And here's our atom data. Looks lovely. So if you had maybe a bit too much noise on the edges of your data, you could use your arrow keys to control these gates. You see the yellow gate here, and you could cut and snip data from your record. If you want to go to the other gate on the other side, you hit Tab, and now this gate is yellow. And now you can hit the arrow keys and move it over in big jumps. If you want to move your gates in small jumps, you hold down Shift and use your arrow keys. And you can see now the gate moves slowly. Okay, I'm not interested in snipping any of this data though, so I'm going to bring it back to full screen. And if you were to snip data, you use these scissors here. You control your gates and then use the scissors to snip. But I want the full spread of data. So I am at this point ready, unless I want to see the data more. I get adjusted up or down. And I'm ready now for SPAC. So I'll click the SPAC icon. And I used a default triangle 10 array with a 50-meter array size. And I laid out this, this survey following the Koichi triangle method, which is shown in the field operations video. So I can just basically proceed with this triangle 10. I could also open up an array file. And what that would look like is I would grab an array file. I've already made generic ones. It's just a text file, a notepad file that you create. And I would go here and I would paste the array file in the root of the data. You don't have to keep it there. It's just easiest to reference it there. And if I actually go and open that, you'll see it's a list of coordinates. 00 is location of serial number 47, the atom serial number 47. This is for the coordinates of 55, then 56. And then we have 61, 62, 65, 67, 68, atom 72, and then our three component atom 35, 0007, which sits in the center of the triangle and has ultimately the highest serial number, so it's the last one in the file. Your array file must be in order of increasing serial number. So depending on how your survey geometry is laid out, this could look different, but you want them all next to each other. This file is space delimited, so you just put your coordinates X here, Y there, and you just put a space between them in order of increasing serial number. I'm going to hit save. This is ready. Again, this is just a text file. I'll exit, and I'll go back to SPAC, and I can click our triangle 10 array file, hit OK, and it'll say number of receiver locations 10, and I get hit OK. It's going to go through a couple prompts, number of traces, number of receivers, number of FFT blocks, number of pairs, number of spacings. This will vary slightly depending on the geometry of your survey. Hit OK. And here's the data that we get. We get the first step of data where you can look at coherency and frequency values and at different depths. This is 5.4 meters. This is 7.9, 8.2. And you see this data looks very nice. It's very clean, very constrained. There's not too much difference. The coherency is very good between all the different geophones. Here it's 22.1 meters, 21.6. Look how nice and clean this is. I'm going to go back though, and I'm going to show that this looks the same using the default triangle option. As long as you set up your atoms and serial numbers appropriately, then that's no problem. So I'm going to hit back, go back to this screen here and hit SPAC again. I want to apply new geometry, yes. Triangle 10, array size 50, and hit OK. Same prompts pop up. And here's our data again. And my, does it look good. We also have one other option. We go back, we get SPAC, apply new geometry, yes, and we could use the GPS here from the atoms. So if you are unsure of your geometry and you don't have a file, you can always click use GPS. Now, I consider this the ultimate fallback because the GPS on the atom has a accuracy of 3 to 5 meters. So for larger surveys, it's fine. For smaller surveys, it's best to use an array file. But we'll hit use GPS here. We'll hit OK. We can see the different prompts pop up. And here's our data again. Not as clean. It's definitely more noisy, but ultimately it looks about the same. So very, very good quality. But it's best to use an array file or the built-in geometry options. So again, we're going to go back. We're going to hit SPAC, use the right geometry, triangle 10, array size 50 meters, hit OK. And my, does that look nice. Okay, so now the next step is to hit phase velocity. So we'll click our phase velocity icon here. If you wanted to before, you could always adjust your gain with the up and down arrows here. And you can also edit and remove certain data here depending on the coherency values of the different geophones. But this is so good, we can go straight to phase velocity. We'll show the maximum frequency to be 30 Hertz. Hit OK. And there is our phase velocity diagram for this survey site. And man, is that awesome. This is the example data that will be on the website. So on the left, we have coherency. On the right, we have our phase velocity diagram. Looks great. You can edit your points within here. You can see I just moved these guys up, right? You can kind of direct them, but it's best to use this line at the bottom. Using this line, you can follow the peak shear wave signal, the peak shear wave velocity for that frequency. So blue is the area of best fit, and we see here that there's this nice curve going up and then going down like this right to here. And there it looks like it jumps up to a higher mode. Here's some other data. Here's background noise from the Earth. Here's some noise at 14 Hertz. I don't know what caused this. But our data right here is very, very, very good. So we'll scroll down right to above that taper and we'll get nearly a perfect match. So I will delete these points. I'll move these points on the next screen. I won't deal with them here. This is such a good fit, I'll just leave them. So if you are fine with the look of your phase velocity diagram and all the points, then you click the curve button here, the dispersion curve. So the dispersion curve icon will open up WaveEq, which is another program used in SeisImager. So we'll click the dispersion curve and it says number of phase velocity data is 490. This is all the different points that we see. There's 490 of them. And do I want to interpolate to reduce data? Do I want to basically remove some of the points just to make it easier to work with? It makes the inversion faster. So I'm going to hit yes, and I'm going to choose 200. There'll be 200 of these circles after I'm done. I hit OK, and if I go full screen, we can see this dispersion curve here, but the scale is really off. So how do I adjust the scale? Well, I use these blue icons up here in the top. So I can make this smaller and bigger using the dark blue icons, and I can make it wider or length. I can make it wider or less wide using these light blue icons. So I'm going to open back up SPACPlus, and I'm going to layer WaveEq on top of it right here. And I like having both in front of me when I do this. So with this curve here, you have a few options. First, you can use a gate to delete data. You can delete data with a cursor, or you can go through some of the options here for deleting data, bad data. So for example, you could do delete higher mode, and you can see a lot of our higher mode data was deleted. I could then use this cursor to highlight over that single point and click the delete button. I could use this cursor over that point to click the delete button. And then I could also use my cursor on these points, but it might be a little easier with a dispersion gate. So I can delete picks outside of the gate. And to control the gates, you just use your arrow keys. And to change gates, you use enter. So I'm going to choose this gate right here at the top of the curve. And then this gate right here is fine already. And I'll hit enter again. And now we have deleted data removed. So this is a very, very nice dispersion curve. We can see the frequency here on the x-axis, 0 to 50. And it gets to about 27.5. And then we can see the phase velocity here. And at a low frequency, the phase velocity, meters per second, is fast. And at a higher frequency, it is slower. It's about 150, settles right just below it. Here also are some waves that show the approximate wavelength that we're getting here. So a frequency of 5 gives us about 200 meter. And if we want to see the depth that this model will be able to generate to, we click VR, which is Show Apparent Velocity Model. So I can click VR here, and we get this nice model, and it looks like we get data to about 75 meters, which is great. So we're going to go back now to display, which is actually dispersion. It's actually the dispersion curve. We'll go back there. And now one last option you could do is you could smooth this data, which I will do. And then I can create an initial model. So you go to MASW MAM 1D, you click this, and you click initial model. Now we decided the depth was about 75 meters. You can choose your layers, your number of layers here. More layers just gives it a little bit higher resolution, but 15 is typically fine. And then you hit OK. This is our initial model, our initial S-wave velocity model with depth. And we can see how well the model fits our curve. And if we want to see our error, our RMS error, we go back to display, and then we hit the red star here, which calculates a theoretical dispersion curve. So we'll click the red star, and now it creates a black line, which is a theoretical dispersion curve based off of the data we have, and the RMS error is 20 meters per second. So not that much error, pretty good, but we can improve it. We can improve it by running some inversions on the data. So there's different types of inversions. You have LSM, which is thickness only. Then you have LSM, velocity and thickness. And then you have these other two. It's typically best to just run the default inversion LSM here. And if we go to VS, that shows us again our velocity model. And we'll go here and we'll start to invert. Now, typically I only run 5 iterations. You don't want to run too many iterations. It just kind of warps the data, but 5 is nice. And we'll hit OK. And this takes some time using the nonlinear least squares method. And this takes longer if you didn't interpolate between your data points. If you are over here and leave all of those there and then you run your inversion, it will be slower than if you space them out a bit more and choose an integer like 100 or 200. So, cutting the number of data points in half is probably just fine. Cutting them in half, more than half, is for a shear wave velocity model, it's doable, but it's better to preserve as much resolution as possible. So this was calculating all the derivatives. It's going through the inversion process. Inversion has completed. The elapsed time is that many milliseconds, but it wasn't that long. Hit OK. And now if we want to see our RMS error, then we go back to Dispersion Curve, DISP1, and we again click the Calculate Theoretical. And now our theoretical dispersion curve has an RMS error of 9.29, so very, very good. And here again is our velocity model. So at this point, we've calculated a dispersion curve, we have a velocity model, we're ready to save this data. So we could go to File and then do Save 1D Phase Velocity or HV data, which we'll do. And we'll navigate to the folder, which is Atom Data, Atom Field Operations, and we'll do Atom Training Video Data. And we'll call it 1, because now we're going to add the HV data to it. So we'll hit Save. And this data is here. You can add more data to it. You can append data to it, and that's exactly what we're going to do. So we're going to minimize this. we have our phase velocity data here, but we can just X back. Here's our common time block. We'll X back out of that. And now we're going to process our HV data. So we have our common time block here set for all of them. To change that, we'll go to Edit, select Single Sensor, because we are only interested in the Atom 3C. And it's already highlighted, but again, to move them, you use the arrow keys and you hold down Shift. And you can up, down, left, right. It all works. So we'll go down to the Atom 3C. And now we can click Common Time Block, the CTB icon. Existing data was cleared. Apply bandpass? No. And here is our 3-component data for HV micronization, ambient noise, data analysis. And same thing with the gates. You can use arrow keys to move those gates over, left, right, tab to go to the next one, left, right. If you want to just move a small amount, just do Shift. So I'm going to cut out a little bit of this noise here because we have 1800 seconds, which is plenty of data for HV. So I move the right gate to cut that. And on the left gate, I'm just going to move it a little bit over here. And maybe this is from me walking by the sensor, creating a little bit too much noise. I'm not exactly sure, but I still have more than 1700 seconds of data. So that's more than 30 minutes. So I'll hit the snips and there's our data. And now if you want to do HV analysis, we go to Analysis here, the Analysis button, and we go to HV Analysis. We click that. HV Analysis traces 3, yes. Go through the prompts. Hit OK. And now we have our HV diagram effectively on the far right here. These ones show amplitude, voltage, and a few other values. So this is basically just a little bit of a data screen. If you like the look of it, here's our HV peak. This is what we'll be working with. From here, you go to HV analysis and you go to show HV curve. And this also launches WaveEq, which is the SeisImager program that we used earlier for the dispersion curves. So we'll hit show HV curve. And it's asking us if we want to interpolate to reduce data. So we'll click yes, and we'll set that to 400. And now here's our HV curve. It looks like to 20 or so, 20 hertz. Or this is actually to about 30 hertz here is our top. And on the left, it goes down to 0.1. And we'll see that our peak value here is right around 1.8, or actually it's right here, 1.777 hertz. So I guess we got good lucky numbers here. Now, if we wanted to change the location of that, you could always go to HV curves and set min and max to pick the max frequency. And it's the same thing here. You use the arrow keys to move these gates, and you'll see if I knock it off, it'll start to move, right, to whatever the peak is within that time window. So I like that location though, so I'm just going to keep the gate here. And I'll hit enter to move the other gate. Just for illustration, you can see I can push it down, and that's our peak frequency now. But this is great data. I would want data within this full range, and that's the peak frequency. So I'll hit enter just to finish that. And this HV data is done. I can make it bigger using these dark blue icons, the arrows. I can make it wider using the light blue. And again, I could go full screen here if I wanted, though I, again, prefer kind of the split screen. And then at this point, we're ready to either save the HV data, or we can append it to the shear wave velocity data and have all the data in front of us in one single file. And that's what we're going to do. So you go to File, and again, you can either save this as a separate file, or, and actually let's do that. So we can just type in HV data. and that would save that HV data by itself. But if you wanted to add it to a shear wave survey, then you could do open 1D phase velocity. This is that RST file we created earlier. And we'll click Atom Training Video Data, and we'll open it. And now you have the option of just opening the new data and getting rid of this, or you can append the present data. So that's what we want to do. We want to append our shear wave velocity and our HV data together. So we'll hit OK. Now it's asking if you want to average the same frequency. This is only if you're appending multiple 3-component sources at once. So it doesn't really matter. We'll just hit no. And here we go. We have our dispersion curve. We have our velocity VS75 roughly a plot. And then we have our HV plot, which we just scale out to see. And we have this all in a single RST file. So I could save this and save over this file here. I'll hit save. And now we have all of our data in one spot. And again, you can do the theoretical curve here. You can do the theoretical on the HV. And yes, this is a completed data set for a shear wave and HV data using a atom survey, doing an atom survey. So we had, again, a single three component atom that we used, and then we had 10 one component atoms, and all together they can give you these results here. So if you wanted to upload to the database, you can use the SeisImager database to upload your data. Then you go right here and you do upload 1D phase velocity data. You log in and you choose your project and you upload it. I'm not connected to the internet right now, so that's why I'm not able to upload it. But that's an individual thing because you have to type in your username and your password. So if you're interested in that, you can go to SeisImager.com right here, and you can use our geophysical database. You can create a password and username and upload your data publicly. Or you can save it all as RST results and model it however you wish. So that is a full processing sweep from download to end result, and I hope that was informative. There are plenty of resources to understand the software more. There's the operations manual for the atom. There is the SeisImager manual, and I encourage you to look through those. But I hope this operations video gives you a good starting point to just hit the ground running, get some data, survey with the atom, and get it downloaded without any hiccups and get it processed. Thank you for watching this atom operations training video, all the way from field operations to data analysis using SeisImager.